Welcome to today's session focused on the utilization of control structures, specifically if statements and loops within the R programming language. Mastery of these constructs is essential for effective programming as they empower you to make informed decisions and automate repetitive tasks with precision. By the conclusion of this session, you will possess a comprehensive understanding of how to leverage these tools to enhance the functionality and efficiency of your R scripts. In this session, we will delve into the fundamental components of if-else statements in R, a key feature for decision-making in programming. Key components. 1. If condition. This evaluates a logical expression to determine if it is true. When satisfied, the code enclosed within the braces is executed. 2. Code block. This section comprises the code that is executed if the preceding condition holds true. It can encompass any valid R code. 3. Else condition. This directs the program to execute a designated code block when the if condition evaluates to false. If-else statements are extensively utilized in data analysis, allowing practitioners to implement different logic or operations contingent upon specific data conditions. Mastering this construct is essential for effective programming in R. Let us examine an if-else statement that evaluates temperature conditions to demonstrate branching logic. We define a variable named temp and assign it a value of 75 degrees. The following conditions will be evaluated. If temp is greater than 80 degrees, the system will print "it's hot outside." Else, if temp is greater than 60 degrees, it will print "it's nice outside." Otherwise, it will print "it's cold outside." Given our defined value of 75, the condition temp 60 evaluates to true. Therefore, the output will be "it's nice outside." This example illustrates how if-else statements facilitate decision-making processes based on specific conditions, a crucial technique in programming for automating decisions in various applications, from software development to data analysis. Nested if-else statements allow for multiple levels of decision-making by embedding conditions within one another, frequently utilized in programming languages for scenarios requiring detailed logical evaluations. Components of nested if-else statements. Outer condition, the primary condition that initiates the evaluation process. Inner condition. This evaluates only when the outer condition is met, allowing for a deeper level of decision-making. Multiple levels. Facilitates intricate logic flows, but should be structured carefully to maintain clarity. Commonly used in scenarios where multiple criteria must be assessed, such as user input validation and categorization tasks. Excellent for creating decision trees in algorithm design, helping to navigate complex logical pathways. Avoid excessive nesting to keep the code understandable and maintainable. Document your logic to support future revisions and ease of understanding for other developers. In summary, nested if-else statements are essential for building sophisticated decision-making processes in programming. Let's transition to the topic of while loops in programming, one of the fundamental constructs that enable dynamic control flow. Key components of while loops. 1. Condition. Check. At the start of each iteration, the loop evaluates a specified condition. If the condition is true, the loop will proceed. Otherwise, it will terminate. 2. Code block execution. Upon a true evaluation of the condition, the code within the block executes. It's crucial that within this block, updates to variables or the state are included to prevent infinite loops. 3. Re-evaluation. After executing the code block, the condition is assessed again, reiterating as long as it remains true, thereby allowing for dynamic iterations that respond to changing inputs or states. Practical applications of while loops. Use cases. While loops are ideal for scenarios reliant on volatile conditions, such as live data monitoring or user inputs, where the number of iterations cannot be predetermined. Avoiding infinite loops. A critical consideration when implementing while loops is ensuring that the loop will eventually terminate by guaranteeing that the condition can eventually be false. Efficiency considerations. While loops can be efficiently utilized in processing large data sets or conducting intensive operations, careful consideration of performance is essential to optimize execution times. Understanding where and how to implement while loops effectively is key to mastering programming logic and creating robust applications. We explore the concept of a while loop in R programming, illustrating its functionality through a practical example. We begin by initializing a variable, x, and setting its initial value to 0. The while loop operates on a specific condition. In our case, it checks whether x is less than 5. If the condition is met, i.e., x5 evaluates to true, the following actions are performed. We utilize the paste function to display the current value of x. Subsequently, x is incremented by 1. The while loop will continue to evaluate the specified condition and execute the corresponding block of code. This process will continue until x is no longer less than 5. Through this example, we demonstrate how a while loop allows for the repeated execution of code, providing an effective means of incrementing a variable and halting processes based on predefined conditions. Let us delve into the concept of for loops in R programming, which are essential for efficiently iterating over sequences of data. The syntax of a for loop involves assigning the current element of a sequence to a specified variable during each iteration, enabling the execution of a defined code block. For loops are crafted to execute the code block for each element within the provided sequence, rendering them particularly advantageous for performing repetitive tasks seamlessly. These loops exhibit remarkable versatility, allowing for iteration over a variety of data structures, including vectors, lists, matrices. The adaptability of for loops makes them a powerful tool for data manipulation and analytical processes. Understanding and adeptly utilizing for loops is critical for optimizing workflows and automating repetitive tasks in R programming. For loop example in R. In this segment, we will explore the functionality of for loops in R programming, showcasing how to iterate through elements of a vector efficiently. We begin by creating a vector named fruits, which contains 3 elements: apple, banana, and cherry. Next, we utilize a for loop to traverse each element within the fruits vector. During each iteration, the current element is assigned to the variable fruit. The print function, coupled with paste, constructs a string output that expresses our preference for each fruit. Consequently, the loop will produce the following output: I like apple, I like banana, I like cherry. This example effectively demonstrates how for loops in R provide a streamlined approach to iterate over a vector, facilitating the execution of actions for each individual element. Nested for loops in R. Introduction. This video delves into the intricacies of nested for loops in R, a powerful construct for performing complex iterations over datasets. The outer loop governs the primary iteration process, dictating how often the inner loop is executed. The inner loop runs entirely for each iteration of the outer loop, allowing for repeated operations across each value managed by the outer loop. It is possible to implement more than 2 levels of loops, which is particularly beneficial for handling complex tasks, such as matrix operations or manipulating multidimensional data. In our example, the outer loop will iterate through the rows of a dataset, while the inner loop processes each column within those rows. This structure is commonly used for tasks such as matrix manipulation, data cleaning, and constructing multidimensional arrays. Nested for loops provide a robust mechanism for executing intricate iterative tasks, especially when working with multidimensional data sets. Mastering this technique will significantly enhance your data manipulation capabilities in R. Practice is essential to mastering control structures in R. Make sure to complete the assignment in Codio to reinforce what you've learned. By consistently applying these concepts, you'll build confidence and develop a deeper understanding of loops, conditional statements, and other control structures. Collaborate with your peers, celebrate your progress, and stay motivated. In our next session, we will dive into Module 2, Data Structures and Manipulation within RStudio. Get ready to explore how to work with vectors, matrices, data frames, and more.